In the previous lessons, we've been looking at limits graphically and numerically. Today we're going to be looking at limits analytically. One of the most common techniques for evaluating a limit is called direct substitution. Now, in order to use direct substitution, we have to make sure we're working with a continuous function. What is a continuous function? For right now, we're going to define a continuous function as a function that is a smooth curve. It doesn't have any breaks or gaps. You could draw the function without lifting your pencil from the paper. So this is an example of a continuous function. So let's look at how we would use direct substitution if we are working with a continuous function. Let's say we have our function here, y equals f of x, and we are trying to find the limit of this function as x approaches a. We know that in order for a limit to exist, the one-sided limits must equal each other. So if we looked at the limit of f of x as x approaches a from the right, as we approach a from the right, our x values are approaching a from the right, we're going to analyze what's going on with the y values. So our y values are approaching this value right here. Let's say that equals some value L. So we would say the limit of f of x as x approaches a from the right equals L. Now let's look at the limit of f of x as x approaches a from the left. As we take values of x approaching a from the left, we're going to look at the associated y values. And we can see, again, it is approaching L. Now that will happen with any continuous function. Our one-sided limits will agree at a. So our conclusion, we can now say the limit of f of x as x approaches a equals L. So that's looking at direct substitution graphically. Let's look at it analytically. So here we have the limit of 3x cubed minus 2x as x approaches 2. We do know that 3x cubed minus 2x is a polynomial function, and all polynomial functions are continuous everywhere. So we can use direct substitution. So the direct substitution technique means that you can just substitute the value of 2 in for all of your x's. So we would substitute 2 in, we would get 3 times 2 cubed minus 2 times 2, which gives us 9 times 8 minus 2, there goes the pen, 2 times 2. That gives us 72 minus 4, which is 69. Fooled you, 68. So we can conclude that the limit of 3x cubed minus 2x as x approaches 2 equals 68. That's using direct substitution because we know we were working with a continuous function. The function is not undefined. Now, if direct substitution is used to try to evaluate a limit and we get 0 over 0, this is called the indeterminate form of a limit. And that gives us some special information that we can use if we get this indeterminate form. So taking a look at this limit, the limit of x minus 2 divided by x squared minus x minus 2, if we tried to use direct substitution, we would get 2 minus 2 over 2 squared minus 2 minus 2, which is 0 over 0. This is called the indeterminate form. What this means is we would have to try to manipulate this expression somehow so we could try direct substitution again. Now we're going to get to some of these types of problems in a little bit, but I just wanted you to become familiar with this terminology. Direct substitution is where if we have a continuous function, we plug in the value for x and try to evaluate the limit. If we get 0 over 0, that's called the indeterminate form, so we're going to try to manipulate this expression and keep it as an equivalent expression, but then use direct substitution to get some value. Let's look at some limit laws before we get into the indeterminate form. Here are some limit laws. I'm just going to give an example of each one of these limit laws so you can get familiar with what it's saying. Take, for instance, the first one. Let's call this number 1. This one, if we had the limit of 2x minus 1 as x approaches some number, let's just say 3, I could rewrite this as the limit of 2x as x approaches 3 minus the limit of 1 as x approaches 3. That's what this limit law is indicating. Same thing with the second law, only this one is for subtraction. Number 3, if I had something like the limit of 2x as x approaches 1, I could rewrite this as 2 times the limit of x as x approaches 1, and we would get the same result. Number 4, if we had something like the limit of e to the x times the sine of x, we could take these limits separately. We could take the limit of e to the x times the limit of the sine of x as x approaches 1. Number 5 is for division. If we're taking the limit of an f of x divided by g of x, well, we can take the limit of the numerator separately from the limit of the denominator, as long as the denominator does not equal 0 when you evaluate that limit. So an example of that one might be if I have the limit of 3x squared all over the cosine of x as x approaches 1. I could rewrite this as the limit of 3x squared as x approaches 1. Evaluate that limit separately from evaluating the limit in the denominator, and I would get the same result. So those are equivalent. Also, here are some more limit laws we can apply when we're working with limits. There is one of them that I would like to discuss. I think number 1 is self-evident. Let's look at number 2, the limit of a constant as x approaches a. Let's look at this one graphically. If I have a constant y equals c, and I'm looking for the limit as x approaches a, do you see why that the limit of this constant as x approaches a would equal c? If we took the one-sided limits, we approached a from the right side of a, we would be approaching this value, which is c. And if we looked at the one-sided limit from the left, approaching a, our y values are also approaching c. Number 3, that could be explained with direct substitution. Same thing with number 4, if you think about it as direct substitution. Number 5, that's an interesting property or a law. If we have the limit of the third root of 3x to the 5th minus 3 as x approaches 1, I can find this limit by taking the limit inside the cube root function and finding the limit of this expression first and then taking the cubed root. And we will get the same, I'm sorry, that should be as x approaches 1 and not 3. So those would be equivalent expressions. We have one more here. I'm going to erase everything so we can see that a little bit better. If we have the limit of p of x, and p of x is indicating we're working with a polynomial function. So if we take the limit of a polynomial function as x approaches a, we can always use direct substitution. These laws also apply to one-sided limits. Now, we saw this back a couple of lessons, and we considered this a definition at the time, but now we're stating this as a theorem. And it's important enough where I wanted to include this theorem now, again, so we see it. If we have the limit of f of x as x approaches a equals some number, we know then that the one-sided limits equal L also. And conversely, if the limit of f of x as x approaches a from the left and the right equals some number, we know that the limit of f of x as x approaches a equals that number. And this is one of the ways we prove that a limit exists, by using the one-sided limits. Here's some examples we're going to evaluate. It says evaluate the following limits. And we are going to be using the direct substitution method because in the first one, we're working with a polynomial. And we know we can use direct substitution because this is a continuous function. Now, if I was to use the limit laws that we just looked at, I could rewrite this as 2 times the limit of x squared as x approaches 4 minus 4 times the limit of x as x approaches 4 plus the limit of 5 as x approaches 4. That's just using the limit laws we learned a few slides back. If you use direct substitution for this first term, we would have 2, and x squared is a continuous function, so we can use direct substitution. We would have 2 times 4 squared minus 4 times, now we're going to use direct substitution again, times 4 plus, now this is the rule that we learned on the prior slide, the limit of a constant as x approaches 4. So that would be plus 5. So we would have 2 times 16 minus 16 plus 5. And that appears that we're going to get 21. Now, we're not going to use these limit laws like this each time. We know we could just use direct substitution on the original problem here. We could just use direct substitution and plug in 4 for all of the x's. And you would see we would get the same result, 21. Now, the next example, we could take the limit as x approaches 2 of x to the 4th plus 3x squared minus 5 divided by, I didn't get the division sign quite low enough, divided by the limit as x approaches 2 of 6 minus 2x. And again, this is using the limit laws we saw on the prior slide. But now we could just use direct substitution. And when we substituted 2 in for our x's, we would get 2 to the 4th plus 3 times 2 squared minus 5 divided by 6 minus 2 times 2. So we could now evaluate this. We'd get 16 plus 12. I'm sorry, this is getting to be a little messy. The pen's not picking up properly down in the corner here. So this we said is 12 minus 5, all divided by 6 minus 4, which is 2. So it appears we would get 28 minus 5 is 23 divided by 2. And again, we are not going to write these limits out using these limit laws. We're going to say this is a continuous function because it's a rational function, so it's continuous everywhere on its domain. So we could just use direct substitution. And you would see if we use direct substitution, we would get what we have right here. And then we would get our 23 over 2. Here we have a piecewise defined function. We have the limit of g of x as x approaches 1, and g of x is defined as x plus 1 when x does not equal 1, and pi when x equals 1. So this would be the graph of our piecewise function. Now, the first part would be a line, the x plus 1, if x does not equal 1. But when x equals 1, it's defined up here at pi. So this would be an open circle right here, and it's defined up at pi. So we're trying to find the limit of g of x as x approaches 1. So let's use our one-sided limits. So if we looked at the limit of g of x as x approaches 1 from the right, our y value is approaching 2. If we looked at the limit of g of x as x approaches 1 from the left, again, we would get 2. Therefore, the limit of g of x as x approaches 1 equals 2. We're not concerned with where the function is defined when x equals 1. It's defined up here at 3.14 pi. But we are only concerned with what are the y values approaching from each side of 1. And they're each approaching 2. Another example. Now when we're evaluating limits, the first thing we always want to try is direct substitution. So if we use direct substitution for this one, we would plug in 0 for all of the h's. So we'd get 3 plus 0 squared minus 9 all over 0, which gives us 0 over 0. This is the indeterminate form. Now this is what I was talking about earlier. We're going to try and manipulate this expression, but write it as a equivalent expression, possibly not at one point, but equivalent every place else, and then try direct substitution and see if we can get a value. So what could we do? Well, let's try expanding the 3 plus h. We would get 9 plus 6h plus h squared minus 9 all over h, and we're taking the limit as h approaches 0. Now we can see that the 9's would cancel, and we could actually factor out an h from the numerator, and we could reduce that h with the h in the denominator. So we would be left with the limit of 6 plus h as h goes to 0. And now we can use direct substitution. If we substitute 0 in for h, we simply get 6. In this example, we actually saw this example back when we were doing limits graphically, and we saw the issue with this one where we couldn't really determine exactly what the limit was for this one because we couldn't interpret the graph. Let's see if we can find the limit algebraically. Now, if we tried direct substitution first, you would notice we get 0 over 0. So what we're going to do is we are going to multiply by the conjugate of the numerator. Now remember what a conjugate is. If I have a plus b, the conjugate of a plus b is a minus b. And when we multiply conjugates together, we would get a squared minus b squared. The middle terms cancel. So in this problem, we are multiplying by the conjugate, but we're multiplying the numerator and denominator by the conjugate because this is just equivalent to 1. So we're not changing the value of our expression. Now what this does, when we multiply the numerator, we'd have the square root of t squared plus 9 times the square root of t squared plus 9 gives us t squared plus 9. The two middle terms cancel, and then we'd have negative 3 times 3 is negative 9. And then we just multiply the denominators together. Now in the numerator, notice that the 9's, they would cancel, and then we would be able to reduce the t squareds. So now in this step we could reduce the t squareds, and we would be left with 1 all over, or 1 divided by, the square root of t squared plus 9 plus 3. Now if we use direct substitution, we'll get a value. When we apply the direct substitution, we would get 1 over 6. Another technique. If we have this rational expression and I use direct substitution, I always try direct substitution first, you would see we get 0 over 0, the indeterminate form. So I'm going to look at this and see if I can factor the numerator. It appears that the numerator can be factored into x minus 1 times x minus 2 . And then I can reduce the x minus 1's, and we have the limit of x minus 2 as x approaches 1, and we can use direct substitution now. Another example. Again, this one appears that when we use direct substitution, we get the indeterminate form. So that tells me I'm going to have to try to manipulate this expression somehow so I can use direct substitution. Again, it looks like I can factor. So I would factor the numerator, x minus 3, x plus 3, all over x minus 3. Now I can reduce x minus 3 with x minus 3. So we have the limit of x plus 3 as x approaches 3, and we can use direct substitution. Now this last example, you might be inclined to use the conjugate. Multiply by 2 plus the square root of x over the 2 plus square root of x. And that may work, but I see a different technique. I think I'm going to try the factoring technique again. The limit of 2 minus the square root of x all over. Now, remember, if I have a squared minus b squared, I can factor it into a minus b times a plus b. I just take the square root of each term. So I could factor this into 2 This would factor into 2 minus the square root of x times 2 plus the square root of x. And you can verify that that's factored correctly. And now we can reduce 2 minus square root of x with 2 minus square root of x. And we have the limit, there goes the pen again, the limit of 1 all over 2 plus the square root of x as x approaches 4. And now we can use direct substitution to get 1 all over 2 plus 2, so we would get 1/4. Show that the limit of the absolute value of x as x approaches 0 equals 0. Now remember, we can rewrite the absolute value of x this way. So if we looked at the one-sided limits, we'd have the limit of x as x approaches 0 from the right. That equals 0. And the limit of negative x as x approaches 0 from the left. That equals 0. And therefore, the one-sided limits agree, so we have shown that the limit of the absolute value of x as x approaches 0 does equal 0. And you can look at it graphically to verify the results. Now this example says prove that this limit does not exist. We have an absolute value of x in the numerator, so we could write this again as a piecewise function. And if we wrote it as a piecewise function, we would have the absolute value of x over x equals. Now notice, this would equal 1 when x is greater than 0, and this would equal -1 when x is less than 0. And if we looked at that graphically, we can see this matches up with our piecewise function. So now we can see where these come from algebraically and graphically. Now, since the one-sided limits do not equal each other, we've shown that this limit of the square root of, of the absolute value of x over x as x approaches 0 does not exist. Here's a piecewise function. This problem here sometimes can catch us if we're not careful. Let's look at the graph of this piecewise function. We have the graph of the square root of x minus 4 if x is greater than 4, and 8 minus 2x if x is less than 4. Notice this function is not defined at 4. So if we're trying to find the limit of this function as x approaches 4, we still can use the one-sided limits to evaluate this, but it is not defined right here at 4. But looking at the one-sided limits, here it's not defined at 4. If we're approaching 4 from the right, we would be using this function, and we can see the y values are going to 0. If we're approaching 4 from the left, which means less than 4, we would be using this function. So that's why here we're using the square root of x minus 4, and for this limit, since we're approaching from the left, we're using 8 minus 2x. And so we can conclude that the limit of f of x as x approaches 4, since the one-sided limits equal 0, this limit equals 0. This is the greatest integer function. We've already looked at this example. If we're looking for the limit of the greatest integer function as x approaches 3, we know the function is not defined here, but up here. So as we approach 3 from the right, we can see we are approaching 3. But if we look at the one-sided limit from the left of 3, we can see we're approaching 2. Therefore, this limit does not exist. Let's summarize what we've done. We always want to try to evaluate a limit, first of all, using direct substitution. If we get the indeterminate form, the 0 over 0, then we can try factoring, expanding, or multiplying by the conjugate. And then simplify the expression, and then try direct substitution again. And when we were working with piecewise functions, we could rewrite, when we had functions involving absolute values, we could rewrite them as piecewise functions and evaluate them on the correct intervals. And then we checked our work graphically.